an equation that expresses an, the general form of the sequence an, in terms of one or more of the previous terms of the sequence is called a recurrence equation or a difference equation. So here let me read again, an equation that expresses an. So here what is an? An is the general form of the sequence. Okay, sequence, you know what is a sequence? That is set of numbers arranged in certain order, okay, or with certain rule. So here you see we call this as Fibonacci. Let us consider that, okay, Fibonacci series. So here you have sequence of numbers 0, 1, 1, 2, 3, 4, 8, 13, etc. And here we can choose a general term an. So that's what the definition says. The general form of the sequence an, and this is read as sequence an, in terms of one or more of the previous terms of the sequence. Okay, general term will be in terms of one or more of the previous terms. So from this you can choose a general term, and that general term will be in terms of one or more of the previous term. So I will explain Fibonacci's sequence of numbers in here in Fibonacci series, so that you will understand what is recurrence relation. You see, Fn is equal to Fn minus 1 plus Fn minus 2. So I have taken F because this is Fibonacci, where n is greater than or equal to 2. Okay, here we can take n as a number which is greater than or equal to 2. And also we have initial condition, F0 is 0, F1 is 1 are the initial condition. F0 stands for the first number in the sequence. What is the first number? 0. So F0 is 0. F1 denotes the second number in the sequence. What is F1? F1 is 1. So let me explain that. Fibonacci sequence, F0 is 0, F1 is 1. That is the first number is 0. Then the second number is 1. So general term we can define like this. Fn is equal to Fn minus 1 plus Fn minus 2. That means if you take the nth term, it is the sum of the previous two terms. N minus 1 denotes the previous term of Fn minus 1 is previous term of F1, and Fn minus 2 is previous term of Fn minus 2. So it is just adding the two numbers to get the nth term. Okay, if you add the previous two terms, you get the nth term. So what about the third term? You have to add the first term and the second term. 0 plus 1, 1. 0 plus 1, you get this 1. Then what about the fourth term? You have to add the previous two terms. 1 plus 1, 2. Then what about the next term? You have to add these two numbers. 2 plus 1, 3. Then what about the next term? 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13. It goes on like this, and this sequence of numbers we can call it as Fibonacci series. Okay, or Fibonacci sequence. So here when we consider this, F0 and F1 are initial, and this particular equation is called as recurrence relation or recurrence equation of order 2. Okay, so this equation, this particular equation, that is Fn is equal to Fn minus 1 plus Fn minus 2. This is called as a recurrence equation or recurrence relation. That is the general term Fn. Fn is the general term. If you take any number, it is sum of the previous two numbers. That is Fn minus 1 plus Fn. Suppose this is Fn, this is Fn minus 1, and this is Fn minus 2. So always when you take Fn, it will be sum of the previous two terms. So it goes on like this. So this general term is defined in this way, and this relation is called as recurrence relation of order 2. So here how will you find the order? Highest term Fn is the highest term, right? So here the this is considered as nth term. So highest term minus, what about the other term we are considering? This is the smallest term, n minus 2, Fn minus 2. In this relation, Fn minus 2 is the smallest term. So we can subtract n minus 2, n minus of n minus 2. We get n minus n plus 2, that is plus and minus will be eliminated too. So order of this recurrence relation is 2. Okay. So to find the order, just to subtract the highest term by the lowest term. You subtract the degree so that you get order of the given recurrence relation. Next definition, homogeneous recurrence relation. Recurrence relation of the form an is equal to c1 an minus 1 plus c2 an minus 2 plus etc. plus ck an minus k is homogeneous recurrence relation. So now let us learn how to solve a homogeneous recurrence relation. First thing, if the roots are real and distinct, say r1, r2, etc., then an is equal to alpha 1 r1 raised to n plus alpha 2 r2 raised to n plus etc. So if there are n roots and there are any number of roots, okay, it depends on the equation. R1, R2, etc. are the root means, then the homogeneous solution, we call it as homogeneous solution. Alpha 1, alpha 2 are constants, and we write alpha 1, R1 is a root, so R1 raised to n, plus alpha 2, which is a constant, R2 is a root, R2 raised to n, plus etc. If you have R3, you can write alpha 3, R3 raised to n, plus etc. Now second case, if the roots are real and equal, R1 is equal to R2, then we write an is equal to alpha 1 R1 power n plus n into alpha 2 R2 power n plus n square into alpha 3 R3 power n plus etc. That means, you see, this power of n is getting increased. Alpha 1, alpha 2, alpha 3 are constants as usual, as in the previous case. R1 raised to n, R2 raised to n, R3 raised to n goes on like this. The difference is, if you have two roots, then it's enough you write 1 and n. If you have 3 roots, you have to take up n square also. If you have R3 as a root, then you have to take n square. If you have R4 as a root, then you have to, what will be the next term? n cube alpha 4 R4 power n. Okay. So n square, n cube, likewise it goes on. So an is, I'll read it again. If the roots are real and equal, like R1 is equal to R2, etc., then an is alpha 1 R1 raised to n plus n into alpha 2 R2 raised to n plus n square into alpha 3 R3 raised to n plus etc. Then if the roots are complex conjugate, alpha plus or minus I beta, then an is equal to r power n alpha 1 cos n theta plus alpha 2 cos n theta, where r is equal to square root of this real part square plus imaginary part square, alpha square plus beta square, and theta is equal to tan inverse of imaginary part by real part. Theta is tan inverse of beta by alpha. So now we will continue with the problems. Solve the recurrence relation. an is equal to an minus 1 plus 2 an minus 2 with a0 is equal to 2 and a1 is equal to 7. So this is homogeneous recurrence relation. Okay. We know homogeneous recurrence relation is of the form an is equal to c1 an minus 1 c2 an minus 2. It's okay. Some of the previous terms we can write an in this form. Then we say it is a homogeneous recurrence relation. So here when you come here, solving part, so recurrence relation here is an minus 1 plus 2 into an minus 2, which is a homogeneous form, and initial conditions are given a0 is 2 and a1 is equal to 7. So now let us consider, coming to the solution part, let me explain. Consider the recurrence relation. Given question, an minus 1 minus 2 an minus 2 is equal to 0. Now let us write the characteristic equation. To write the characteristic equation, we need the order of the equation. Take the highest highest term is an, smallest term is an minus 2. So you can subtract n and n minus 2. So you can write like this, an is there, an minus 2 is there. So n minus 2, we get n minus n plus 2. So here order is 2, okay. Order of the recurrence relation is 2. So you have to start the equation by r square. So now I write the equation in r. What about the equation an minus 1, an minus n minus 1 minus 2 an minus 2 is equal to 0, right? So this particular equation, so this is the given equation. In the given equation can be rewritten. You can take the coefficient here. What about coefficient of an? Coefficient of an is 1. So you can write 1 here. What is coefficient of an minus 1? Minus 1. What about coefficient of an minus 2? Minus 2 is equal to 0. So you see order is 2. So you have to start with r square. Second term is r raised to 1. Third term is r power 0, which is constant. So 1 r square is r square minus r minus 2 is equal to 0 is the characteristic equation. So you should know how to form the characteristic equation first. Okay. How to form the characteristic equation? First you consider the given equation. What is the given equation? Given equation is an minus 1 minus 2 an minus 2. Find out the order of this equation. How will you find the order? Order can be taken as the highest suffix of the highest term minus suffix of the lowest term, n minus 2, which is 2. So here order is 2. So once you get order as 2, you can start with 2. We write the equation in terms of r. So you take the coefficient of the given terms 1 minus 1, okay, 1 minus 1 minus 2. So here these are the coefficient. Using this coefficient, let us form the equation using this coefficient 1 minus 1 and okay 1 minus 1 and minus 2. We can write 1 minus 1 and minus 2. You have to write the equation in r. So we take r. What about the order? Order is 2. So we have to take the highest order here, r square. So next to r square, lowest term is r raised to 1. Then r power 0, which is a constant term. So anyway, you get the equation like this. And here, this equation is nothing but r square minus r minus 2 is equal to 0. This particular equation is called as characteristic equation. And now you know how to solve a characteristic equation. Okay, r square minus r minus 2 can be factorized as r minus 2 into r plus 1 equal to 0. Therefore, r is equal to 2 and r is equal to minus 1. R minus, you get equation r minus 2 into r plus 1 is equal to 0, r minus 2 is equal to 0, comma, r plus 1 is equal to 0, r is equal to 2, r is equal to minus 1. So these roots are real and distinct, okay, real and distinct roots, real and different roots. So what we are going to do, the solution will be of the form, just now we learned an is equal to alpha 1 r1 power n plus alpha 2 r2 power n. So we can take the first root as r1, second root as r2. So our solution is alpha 1 2 power n plus alpha 2 minus 1 power n. Okay. So we get this alpha 1 2 power n plus alpha 2 minus 1 power n. So using this first case, if the roots are real and distinct, then we take alpha 1 r power n plus alpha 2 r2 power n plus etc. Here we have only r1 and r2, so we take only the first two terms and we get alpha 1 2 power n plus alpha 2 minus 1 raised to n. Okay, so that is the solution here. So here we get the solution like this, alpha 1 plus alpha 2. So now an is the solution, but one more thing, you have to find alpha 1 and alpha 2 because the initial conditions are given. What are the conditions given here? The conditions are a0 is 2 and a1 is 7. So when a0 is 2, A0 is 2 means we can take this suffix n is 0. Okay. General form is an. So n is 0. When n is 0, answer is 2. So let us make the substitution. Take the given equation. That means the solution. An is equal to alpha 1 2 power n plus alpha 2 minus 1 power n. And in this equation, what you are going to do is, we have to substitute n. A0, so n is equal to 0. Just compare it with this. N is equal to 0. So when n is 0, this becomes A0. And here when n is 0, alpha 1 2 power 0. And here alpha 2 minus 1 raised to 0. And this is equal to 2. Why do we equate it to 2? Because A0 is given as 2. So when you put 0 for n, it becomes A0. And here also 0. 0, and this is equal to 2. Okay, we can equate it to 2 here. So now this implies, we equate A0 to 2. Now this implies, what is 2 power 0? Any number power 0 is 1. So you get alpha 1 plus alpha 2, because minus 1 raised to 0 is also 1. Number power 0, these two numbers, it becomes 1. So you get only alpha 1 into 1, which is alpha 1. Plus alpha 2 into 1, which is alpha 2, which is equal to 2. So this is equation number 1. So now similarly, let us take the second condition. What is the second condition? A1 is equal to 7. A1 is equal to 7. So here instead of n, we have to substitute A1. Okay, A1. N is 1. So you substitute n as 1 in this case. So here A1 is 7 is given. This is the solution. This is the solution, right? We got the solution. Equation number A is alpha 1 2 power n plus alpha 2 minus 1 power n. So you take that alpha 1 2 power n plus alpha 2 minus 1 power n, and n is 1. When n is 1, it becomes A1 alpha 1 2 power n is 1 2 power 1 plus alpha 2 minus 1 power, since n is 1 minus 1 power 1 is equal to 7, because when n is 1, this becomes A1, and A1 is nothing but 7. So equate this A1 to 7 here. So now again alpha 1 2 power 1 is 2. So 2 alpha 1. Here also plus into minus, minus 1 alpha 2. That is minus 1 power 1 is minus 1. Minus into plus minus alpha 2 is equal to 7. Now this is equation number 2. So we have equation number 1, alpha 1 plus alpha 2 is equal to 2. And equation 2 here. So now let us solve 1 and 2. 1 implies alpha 1 plus alpha 2 is equal to 2. 2 implies 2 alpha 1 minus alpha 2 is equal to 7. And now you can, adding these two equations, you can eliminate alpha 2 will be eliminated. Plus alpha 2 minus alpha 2 will be eliminated. You get alpha 1, 2 alpha 1 is 3 alpha 1. Okay, 3 alpha 1 is equal to 7 plus 2, 9. So eliminating alpha 2, adding alpha 1, 3 alpha 1 is equal to 9. Alpha 1 is equal to 9 divided by 3, which is 3. So after finding alpha 1, we can substitute it in equation number 1. So if you substitute it here, alpha 1, you can find alpha 2. Alpha 2 is 2 minus alpha 1. Okay, from this equation, what is alpha 2? 2 minus alpha 1. 2 minus alpha 1 is 3. 2 minus 3 is minus 1. So we get alpha 2 as minus 1. So after finding alpha 1, alpha 2, what we are going to do is, we are going to substitute it in the final solution, that is equation A. Okay, this is equation A, that is an is alpha 1 2 power n plus alpha 2 minus 1 power n is our solution. We used the initial conditions to find alpha 1 and alpha 2. Now let us substitute it in the place of alpha 1 and alpha 2. So we get, you see, alpha 1 is 3, alpha 2 is minus 1. So 3 2 raised to n minus. So alpha 2 is minus 1. So minus 1 minus 1 power n. Therefore the solution is an is equal to 3 2 raised to n minus 1 power n. Alpha 1 is 3, alpha 2 is minus 1. So this gives the solution of the given recurrence relation.